So for the second talk, we have the pleasure to have Sophie Donnet from INRAE. So she worked on a probabilistic model and inference methods for ecology and life sciences, and today she will talk about probabilistic model for generalized multipartite networks with some application to ecology. So Sophie, the stage is yours.
Okay, thanks for inviting me. So I will present a joint work with Avner Barren and Pierre Barbillon. Indeed, it's a probabilistic model for generalized multipartite networks. So I will try to introduce the problem, which comes from ecology. So first, networks, they are used in many fields, but in particular in ecology, when you want to study the interactions between agents, and in ecology, the agents are species, for instance. And you study a particular relation, for instance, pollination. So we will gather data of interactions, and from a statistical point of objective, we'd like to study the structure of these networks, and more precisely, would like to find heterogeneity in the way vertices interact. We assume that from an ecological point of view, all the species are not equivalent. Some of them may be generalist, some of them may be specialist, and we assume that the structure of the network will have an influence on the way it will react to for instance, the disappearance of a species or something like that. So we would like to study that structure. So for a simple network, it has been done since many years, but now people are more focused on complex network. For instance, they have worked on multiplex network, where we study in a subset of species two different types of interactions, for instance, pollination and co-occurrence. And people also have had a look at time and evolving networks. And in that work, we'll focus on multipartite networks. So generalized multipartite networks arise when the entities, the vertices, at stake can be in advance partitioned into groups defined by their nature. And these groups, I will call them functional groups. The simplest multipartite network is a bipartite network, where you would observe plants in interaction with pollinators. In that case, my two functional groups are plants and pollinators. And plants and pollinators have special, I cannot consider them as the same type of nodes, so I like to take it into account in my study. However, people started to say that, well, the same plants can be in interaction with pollinators, flower visitors, but also with seed dispersal birds or ants. So in that network, I have four functional groups: the plants, pollinators, seed dispersal birds, and ants. And the method we propose is also able to handle what we call generalized multipartite networks, where the interactions may also be observed inside a functional group. So we can observe interactions. We are interested in interaction between functional groups, but also inside functional groups. So please interrupt me if you have any questions. statistique essentielle agricole?
Yes, please. Everyone should remember to turn their microphone off.
Yes, it's Estelle.
Okay.
We'll cut her. Shut off our microphone. So the data set that motivated our work was gathered by Wesley Dattilo. He's a researcher in ecology in Jalapa, Mexico. And he was interested in the interactions between, well, as I said, plants, pollinators, plants and ants, and plants and seed dispersing birds. So it's a data set that take a long time to gather because, well, you have to have students that will go on in the, well, along the coast, and they will note if they see a plant I and animal J in interaction. And we will consider binary interaction at that point, assuming that if plant I and animal J were seen at least once in interaction, we will consider that they are in interaction. And so this is the network they gathered. So it's pretty a mess. You have here the squares here, the green are plants. You have pollinators, protective ants, and seed dispersing birds. And well, this big network, what I call multipartite network, you can also represent it as 3 bipartite networks, but the plants here are the same. Well, some of the plants do not interact with seed dispersing birds, but globally, all the plants may interact with all the animals. You can also represent your data as a matrix where you put in rows the plants, in column, well, you have a block of ants, your block of birds, block of flower visitor, pollinators, and you put a small square if you see at least both living species in interaction. And well, starting from that messy network or that messy matrix, I'd like to highlight some patterns. I'd like to be able to cluster nodes, so species, sharing the same connectivity patterns, because they will correspond to ecological functions and roles, as I said before. So for networks in general, there may be social networks, you have 2 possible approaches. You can consider classical metrics. In that case, you will try to detect pre-specified patterns, for instance, modularity. You will want to see if you have communities, centrality, nestedness. Or you can consider a probabilistic approach, considering that your network is the realization of a probabilistic model, which in my case will be a mixture model. In that case, I will try to find patterns without any prior assumptions on the type of patterns I'm looking for. I will use that second strategy. I will propose a new probabilistic mixture model, which will be adapted to generalized multipartite networks. And what I hope to obtain is a multi-clustering of the nodes. I will assume that each functional groups, the plants on the one hand, the ants on the other hand, and the birds and the flower visitor, I will partition into blocks, clusters that will gather nodes which will share the same connection behavior in all the clusters, all the networks I observe. So how can I do this? Well, the model we propose is an extension of two existing models, which are called stochastic block models and latent block models. And it's quite easy to understand. The only thing that I have to do is to describe well my observations. Well, I will assume that I have Q functional groups in interaction, and my multipartite networks is a collection of networks involving a pair of functional groups. Okay, and I will, in that work, I will consider binary networks, meaning I have or I have not interaction. It's 0 or 1, but everything has been extended to weighted networks. So I will encode each network, each subnetwork in a matrix XQ Q prime. And in that matrix, I will put 1 on line I and column on row 1 and column A prime. I will put a 1 if entity I of group Q is in interaction with entity A prime of group Q prime. So that said, so this is my matrix. As I said, it's first matrix involving functional group 1 and 2. Oh, sorry, it's 1 and 2, 1 and 3, and 1 and 4. And now I'd like to introduce clusters. So I will assume that each functional groups, pollinators, ants, birds, and plants are divided into, KQ blocks or clusters. The clusters, I encode these blocks with latent variables Z, and ZIQ will be equal to K if individual A of functional group Q belongs to cluster K. Okay, so I divide each functional group into small clusters. I encode that with independent latent variables, and now once I have divided each functional group into clusters, I will assume that two entities will interact. I will observe an interaction between A and A prime with a probability that now only depends on the groups, the clusters, the blocks they belong to. Okay, so I'm assuming that I do not see them, but I have groups. It's like any mixture model. I have groups, and now two individuals in the same groups will interact with other species with the same probability. So it's a generative model. So just look at this illustration. I have my plants, my pollinators, birds and ants, and I assume, you see, I have levels of green. I have dark green and light green, and I have which represents the blocks inside the groups of plants. The same for pollinators. Birds, I have two types of birds, and now the probability for two species to interact depends on the color of the blocks they belong to. Okay, so our model is a straightforward combination of a stochastic block model and latent block model. The difficulty was to formalize what was a multipartite network and how we could handle any type of structure. I wrote it with, well, a Bernoulli distribution because it's 0 and 1, but I can consider any distribution adapted to the data. If what you observe is a number of interaction, well, you will prefer Poisson distribution. If it's a strength of interaction, maybe you will prefer a Gaussian distribution. Well, we have a catalog of distributions that we can use. And well, what about my model? Well, conditionally to the latent variables, matrices and trees are independent. It's in my model. It's an assumption. Conditionally to the latent variable, the entities will connect in an independent way. However, since I do not observe the latent variables, I have to integrate them. So, and once I have marginalized against the latent variables, I introduce dependencies between the entries. Indeed, when I observe the entries of a row A, well, all the row depends on the belonging of node A, and it's different from a standard mixture model. I don't know if you are familiar with standard mixture model, but we have more dependence in that model. And that way, since, for instance, the plants in my example is involved in all the matrices, well, I am also building a dependence, a stochastic dependence between the matrices. The consequence is that if I now I will fix my data and observe what are the clusters depending on the data I have observed. Well, this distribution is really complicated because there is no independence. Okay, so if I want to have the a posteriori best clustering, well, this distribution will be complicated because I have a lot of dependence between the latent variable involved by the fact that the mixture is on the interaction, while the clusters are on the nodes. So I don't know how many time I still have. Well,
you still have like around 15 minutes.
Okay, so the estimation from a statistical point of view, I have my observation of my matrix, and I will assume that my matrix is the realization of the model I presented. And now, given that observation, I'd like to, well, go back to the parameters of my model, which are the parameters of the mixture, the parameters of the connections. But also, I'd like to get the clusterings, which are encoded in the latent variable Z. And, well, everything I said before depends on the number of clusters I consider inside each functional group. And I have a model selection problem, which is what are the best number of cluster of blocks I should consider. So we have two problems given the number, assuming that the number of clusters are fixed. I have to well, estimate the parameters, and I have a model selection problem, which is how can I choose the number of clusters. So as a statistician, I will first write the likelihood of my observations. Well, the model, if I consider what I call the complete likelihood, meaning the likelihood and the joint distribution of the observations and the latent variables, well, it's really easy because, well, I will consider the two terms, the conditional distribution of the observation given the latent variable and the distribution of the latent variable. And as I said, I assume that the clustering are independent. So it's like a multinomial distribution here. It's really easy to write. And conditionally to the latent variable, I'll assume that species connect independently. So this distribution is only a product of Bernoulli distribution. So everything is easy to compute. It's really quick to compute. So I have no problems if I could have the clustering, the latent variable Z. However, I only observe my matrix, my network X. So the likelihood of my observation is equal to the complete likelihood, but I have to integrate that quantity against all the possible clustering. So as you can guess, the number of possible clustering becomes quickly impossible to calculate. Well, it's on a paper you can calculate it. However, computationally it becomes really, really heavy as the number of functional groups increases and also the number of clusters in each functional group. So I'm not able to compute in a reasonable time the likelihood for one given set of parameter theta. So imagine if I want to maximize the likelihood with respect to theta. So in that case, we have a standard tool, which is the EM algorithm, expectation maximization. However, in my case, it won't work, and I will have to consider a variational version of the EM algorithm. So I think I have time just to explain. The EM algorithm is a two-step algorithm where on the one step I will compute the expectation of the complete log likelihood. So here it's a complete log likelihood. This is easy to compute, and I will compute this. I will calculate its expectation once the latent variables have been integrated, but under its distribution given the data. And at the second step, I will maximize that quantity. So it's I won't go back to that. It's really standard. We can prove that iterating these two steps leads to increasing of the likelihood. And if I choose well the initial point, I hope that in the end I will obtain a one of the local maximum likelihood. However, in my case, this distribution here, as I said, of the latent variable given the observation, well, this calculation is really easy if these latent variables are independent. However, in my case, as I said, they are not. So I have no simplification when I want to do this calculus. So it's impossible, once again, because of the same reasons I said before, I won't be able to do this. Well, that's why we will consider people consider the variational EM, which is a quite simple idea and quite magical trick. The idea, I want to maximize that likelihood, and well, what I can say is that for any other distribution of the latent variables, this is a true distribution, the true Poisson distribution of the latent variable. R is any distribution on the latent variable. Well, I can say that the log likelihood minus the Kullback Leibler divergence between these two probabilities, these two distribution is a lower bound of my likelihood. And the idea is that instead of working on the log likelihood, I will, well, maximize that quantity. And, well, that quantity, the thing is I can, well, just applying Bayes' formula, I can transform it into an expectation of the complete log likelihood, which is, it likes a log, there is a log here, so complete log likelihood with, I will take its expectation against this R distribution, which is an approximation, plus the entropy of this distribution. And so this quantity I won't be able to calculate because I don't know the true, well, I'm not able to express the true posterior distribution. But when I have a look at this, well, this is as a last line, well, if I choose, well, the R, the distribution R, well, I will be able to do the calculus. And, well, instead of maximizing the log likelihood, I will maximize the lower bound. And, well, I will choose, for R, well, a family of distributions that such that I am able to compute the expectation. So what was the problem is were the dependencies between the latent variables. So I will consider that in the posterior they're independent, and well, it will work. In a paper, Bickel and co-authors prove the consistency of the rational estimators for stochastic block model. It has been extended to Bipartite block models. So I am able to write an algorithm which will maximize, well, which will maximize a lower bound of the likelihood, and I will do everything so that that lower bound is not so far from my true likelihood. Now, if I want to perform model selection, well, to choose a number of parameters, there is a big principle in statistics in that I want a model that fits well to my data, but I don't want it to be too complicated because otherwise I will have a lot of uncertainty. So the idea is to consider a criteria that we hope to be maximum. So in general, I take the likelihood and I will remove the log likelihood and I will remove a penalization. In our case, I'm not able to compute the likelihood, so I will replace it by the expectation of the log complete likelihood in the same spirit as versional Bayes. And the penalty we are able to compute depends, it takes it as that form. Well, it has two parts. On the left, this penalizes the clustering part. It depends on the number of nodes and the number of groups I want to do in each functional group. And the right term, the right term penalizes the connection part of the model. So it depends on the size of the matrices, which is here, and QQ prime, and the number of connection parameters I've introduced to my model. And well, we should compute that for any size, any size of any number of blocks in each functional groups. Obviously, it's a heavy task because we have a lot of combinations, so we prefer a stepwise algorithm to select the best model. Well, we applied it in ecology. So on the data set I showed before, And you see, in ecology, we have small networks. So we have until now, we had small networks. And what we find is that we have, our algorithm run in a few minutes, and we have 7 blocks of plants, 2 blocks of pollinators. We don't see any difference between the birds. So we have 1 block of birds and 2 blocks of ants. And I can reorganize my matrix. I had it, I don't know, really before. This was my matrix as they gave to us. And so we are reorganizing it by clusters. So we can make groups of plants. And for instance, if you consider the first plants here, well, they only connect to birds. The second groups of plants only connect to ants. And well, for instance, here I have plants that connect to some flower visitors and a few birds. And so I can propose like a mesoscopic view of my network, where now one node is one cluster. The size of the node is proportional to the size of the clusters I have found, and the width of the edges are proportional to the interaction I estimated. Now with what I will do, well, that's the end of our method at that point. However, what people will do with that is that we are now ready for ecological studies, which is, for instance, we will study robustness, or we'll compare networks gathered from several places and see if they are not the same species, but maybe they have the same global mesoscopic structure. So our method, in a few words, supplies clusterings for what we call generalized multipartite networks, and we are not looking for a special structure. We only want to gather the nodes that interact in the same way. So it's now published, and if you want to try it, we now have an R package. The one where you only find multipartite is called Gremlins. It's on the crown since like last week. But we are also with my colleagues from INRAE MEA Paris, and some people working in INRAE Econet. We are working on ecological networks. Well, we are trying to write a new package which is called SBM, and where we hopefully will gather all the block models we are developing to analyze, well, simple networks, bipartite networks, networks with missing data, etc., etc. Multipartite, multiplex. Well, we are trying to gather all the models we are developing in a single package, which is called SBM. Our model is able to handle any structure of generalized multipartite. You can combine binary and weighted interactions. You can have interactions inside the functional groups, or only between two different functional groups. Or we are able to handle missing data. Assume that, well, some species were not observed, or because, well, they were not there. Then you can have matrices of different size. However, we have a big problem, is that our method is only suitable for 1,000 entities. We at that point, we are only able to handle small networks. And the problem is that we now have new methods to obtain networks, ecological networks, and these methods are based on metabarcoding. And in that case, with metabarcoding, you observe a lot of species. So it's more a few thousands. And so we will have to be able to handle larger networks. And well, we are also working on other structure of multi-thing networks. So, and I think it's all I had to say. The only thing is, if you have, well, networks that you might think you could want to analyze with that type of tools, please come and see us.
Thank you very much, Sophie, for the nice, very interesting presentation. So, is there any questions in the audience? Maybe I can start with one. So, one thing that I've been wondering was, like, is there any chance to extend these kind of models to have some kind of hierarchical clustering for this? Because in a sense, you kind of you have a interaction between species. You learn some groups, but you might want to have like zoom in or zoom out and see like yeah. And is there any ideas on how to extend this? I mean, or maybe it already exists in this
well, I think I think there are some models. I don't remember the name, but I think some people have had a look at that type of models. But yes, you could assume that, yes. I think it would. You could have clusters of clusters. Since it's a hierarchical model, you only have to say that, well, you only have to write in a probabilistic way the way that the fact that you want to divide a cluster into several other clusters. So I think maybe if it's not done, we could think about it, but yes.
All right, and maybe I had another question about the parameters. So you said that you are selecting the parameter based on the EM model for the number of clusters, I guess, if I understood correctly. And I mean, did you like, how do you evaluate if you found the right number of clusters? And I mean, how confident you are that how do you make sure that
the number of clusters is selected by a penalized criterion.
Yes.
So the EM algorithm is there to maximize the likelihood, and then once I have maximized the likelihood, well, I compute the maximum likelihood, and well, I penalized it more or less because I don't use the true likelihood, but well, and well, it's like any penalized likelihood criterion. We tested it a lot. one thing, and then Christine, who is there, is writing a paper on its theoretical properties from an asymptotic point of view. Then the study is like likelihood criterion. So you have only one and the theoretical point of view, and then, well, we made it work on simulation studies and things like that.
Yeah.
Okay, so on simulation studies,
if I can add some word?
Yeah, go ahead. Go ahead.
Yes. So for the moment, it's still a conjecture that ECL can be consistent to recover the same number of clusters. So, but we usually use it for these models. I take the opportunity, Sophie, to thank you for your presentation. I have just a quite a little question about identifiability. Is it straightforward for your models?
Yes, it's exactly the same as, well, up to label switching. The proof is, well, we didn't do it because it's really painful, but it's really like any stochastic block model.
Okay, thank you.
Because you have one parameter per matrix. So yes, it's like Bipartite or any, yes, there is no difficulty at that point.
Okay, thank you.
Yeah, and thanks a lot for the number of clusters. So what you said also, you did a lot of simulations, and on the simulation you are able to find the right number of clusters with this penalized criterion.
Mm-hmm. Mm.
Okay. Because I mean, this is something I have kind of similar problems with some dictionary learning, where you need to find the number of atoms that you put, and this is really like finding the right method to evaluate this kind of stuff is always
Yes.
not so trivial.
No.
All right. Is there any other questions? So if there is no other question, I think we will wrap up here. Thank you very much for both speakers for presenting and accepting our invitation. Thanks everyone who attended the talk, and the next Palaisien seminar will be on the 5th of January, and we already have a program. So if you're interested, please go on the website and don't hesitate to already register, so we kind of know who's the audience. And yeah, thank you very much, and see you all at the next session.
Yes,
Thank you very much for the nice talks. Thank you.